Yesterday, we talked about electric potential. We talked about electric potential energy difference, and we talked about electric potential difference. So 4 terms. We want to go through all 4 of those terms again today just to refresh your memory. And then we'll take a look at the homework that we had on page 565 to illustrate a couple of those terms. First one, electric potential energy. We defined electric potential energy as the energy stored in the system of 2 charges a certain distance apart. So let's say Emma is one charge, Simon is another charge. They're going to either attract or repel each other. That means there's going to be a certain amount of potential energy in the system of Emma and Simon a certain distance apart. All right? That potential energy is analogous to gravitational potential energy. Okay, when I drop this pen, it falls toward the earth. It has potential energy. The system has potential energy because the reality is the earth actually rises toward the pen a little bit as well, just not very much. Okay, the energy stored in the system of 2 charges a certain distance apart. Symbol for electric potential energy, EP. Done. All right, next term. Electric potential energy difference, or the change in electric potential energy. There's not much to define there. Okay? It's the difference between the electric potential energy one spot versus another. The symbol, of course, is going to be delta EP. If EP is potential energy, then the change in potential energy will be delta EP. But what else can we write down as a symbol for the change in electric potential energy? What else means the same thing as the change in electric potential energy? Maria? Work, good. The work done against an electric field is equal to the change in the electric potential energy. There's actually another equation that we can put in here all at the same time. Delta E is equal to work, but work is also equal to, think back to physics 20. Force times displacement, right? The electric force that acts on the charge, the electric force that's required to move that charge over the distance over which that charge is moved. So potential energy difference. Now we're going to talk about electric potential. Not potential energy, but rather potential. Sounds the same, but isn't the same. It's related, but it's not exactly the same thing. Who can tell me what potential is in reference to electric potential energy? Remember we gave you an example yesterday. There was 13 of you in the room, and what did we say we had? How much money did we say we had? $52 or something like that? $65? Okay. So the potential energy yesterday would have been the $65, right? That's the total energy that we have. Okay. Energy is what allows us to do stuff. Okay. Money is what allows us to get stuff. We had $65 worth of energy yesterday in the analogy that I gave you. How much potential did we have yesterday? $5, right? The potential given by the symbol V, capital V, was $5. The potential was the money per person or the energy per charge. So the equation for electric potential, the energy per charge, is going to be E, okay, what we have up here, the 65, over Q, the number of charge, the amount of charge you have, the number of people that you have in the room here. 65 over 13 gave me a potential of 5. Each person had $5. The symbol for, or the units I should say, for potential were also V. Kind of weird. The symbol is V, but the units are also V. Potential, and then the units are volts. And the last term that we talked about was potential difference. The electric potential difference, of course, is going to be delta V. Now, there's 2 equations that describe the difference in potential between 2 spots, the difference in energy per coulomb between 2 spots. The first one is pretty obvious, and that's good because it's not on your data sheet. Delta V is the final minus the initial potential. The second one is a little bit less obvious, but the good news is that one appears on your data sheet. If V is E over Q, then delta E is going to be delta V is going to be what? Delta E over Q. Both of these give you the exact same result. Use whichever one happens to fit the givens that you have the best. Now, we defined one more thing. It was kind of an aside. It wasn't really closely related to any of these four things. It was just one of those things that we had to know kind of as background to solve some of these problems. We talked about an electron volt yesterday. An electron volt. Just like meters per second and kilometers per hour are both units for speed, then joules and electron volts are both units for energy. So an electron volt is a unit of energy. It's defined as the amount of energy that's required to accelerate an electron or proton across a potential difference of 1 volt. So that ended up meaning that the electron volt was equal to 1.60 times 10 to the minus 19 joules. Not 1.6 times 10 to the minus 19 coulombs. It's not a coincidence that it's the same number. When we go through the math, it's going to work out to be the same number every time. But it's not the same thing. A joule is not the same thing as a coulomb. Okay, 1 electron volt is a unit of energy. It's equal to 1.6 times 10 to the 19 joules of energy. All right, your homework last night was page 565, just a couple of questions. Let's take a look at those two questions now. Any issues with either of those? Good. I see Daniel's shaking his head back there. Nope, got him easy. Everybody else is good too? All right, let's try this one. This one looks a little bit more complicated because we got a crazy diagram here where we have two parallel plates. We have something at position A and B. Tell me what this is at position A there. 2.0 times 10 to the 3 Vs. 10 to the 3 volts. What's given to me there? Kristen, what do you think that is that's given to us there at position A? Okay, let's read through the question. A small charge of 3.2 times 10 to the minus 19 coulombs. That could be an alpha particle, or it could be something else. It's just some kind of ion that has a couple of extra electrons, or a couple of extra protons. It's moved between two parallel plates from a position with an electric potential of 2.0 times 10 to the 3 volts. The potential, that's what we start with. Not potential energy, that would be E. Not potential difference, that would be the difference in potential between two spots. The initial potential is 2 times 10 to the 3. It goes to another position with a different potential of 4.0 times 10 to the 3. That's going to be VF, the final potential. Again, not potential energy, just potential. Simon? Why couldn't it be the other way? Because we're going from this one to this one. So initial and final. The reality is, Simon, if you mix that up, you're probably going to be okay because you're going to get the same number. It's just going to be a negative value. And when you get that negative value, it probably just won't make sense when you get your answer. So you're probably going to be okay even if you do mix it up. Wait a sec. There's no question here. Somebody check on 566 real quickly to see what they actually asked. Doesn't look like I've copied over the whole thing into the notes here. Devin says we're looking for the potential difference, which is delta V, right? Okay. Is there anything else? Okay, so we're also looking for the potential energy gained in joules and electron volts. What symbol are we looking for if we're looking for potential energy gained? We already said we're looking for potential difference, which is delta V. Potential energy gained would be what symbol? Emma, you look like you're just about ready to give me an answer there. E, close, not quite E though. Go ahead. Simon? Delta E. We're looking for delta E, right? The potential energy gained. We're looking for the potential energy, that would be E. Potential energy gained would be delta E. And we're looking for that in joules and electron volts. All right. Delta V is pretty straightforward here. right? We've got VI, we've got VF. Let's subtract the two. VF minus VI gives me 2.0 times 10 to the 3 volts. Anybody have a suggestion as to how to find delta E here now? Okay, we've got the change in potential, the potential difference. That would be like going to 7-Eleven. Each of us spent $2. The potential difference would be 2. The change in potential energy per person. The change in money per person. Now we're looking for the change in energy total. Not the $2 that each of us spent, but the total that we spent as a class. Good. Delta E is equal to Q times V. It comes from the equation delta V is equal to delta E over Q. We rearrange that. We get Q times delta V. So we got 3.2 times 10 to the minus 19 coulombs. I almost put 1.6 times 10 to the minus 19 coulombs. The reason I did that, the reason I almost did that, is because that's a really, really common amount of charge, right? The charge of an electron. If it's a multiple choice question, that's going to be one of your options because it's a common mistake. Keep your really close attention, especially when you have a charge that's different than what you usually use. We multiply those together, we end up getting 6.4 times 10 to the minus 16 joules. 6.4 times 10 to the minus 16 joules. But we were also looking for this in electron volts. Pay really close attention to what I'm about to do. As soon as I'm ready to do it, that is. There we are. The technique that I'm going to use to do this conversion, a conversion that you've never actually done before, is so useful in doing any conversion that you have to do. Okay, if you're ever given, I remember on a diploma exam one time, you had to convert pounds to kilograms. And you were given the conversion factor. It said 1 kilogram is equal to 2.2 pounds. So you were given that conversion factor. But people are in their minds saying, do I multiply or do I divide? You don't have to know whether you multiply or divide if you use just a little ratio here. We're going to say 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So if this is equal to this, then this is equal to this. Does that make sense? And if the top is equal to the bottom, which it is, because that's on your data sheet, then the top is equal to the bottom over here as well. When we do that math, let's solve for x there. It works out to be, what is it? 4,000? And we can round that to 4.0 times 10 to the 3 electron volts. And you can see why sometimes it's more convenient to use electron volts. You're not dealing with a number that's 10 to the minus 16. You're dealing with a number that's 4,000. You have a lot more manageable number than 10 to the minus 16. Sometimes it's convenient to use electron volts, especially when we're dealing with subatomic particles like electrons. Sometimes it's not convenient. All right, try those two questions, please, on 566. All right, guys, number 2 says an electron moves between two positions with a potential difference of 4 times 10 to the 4 volts. Let's write that down for number 2 as delta V, 4.00 times 10 to the 4 volts. The charge, because we're dealing with an electron, is 1.60 times 10 to the minus 19 coulombs, and we're looking for delta E. So it seems pretty straightforward. Once we recognize what we have given to us, it seems pretty straightforward. Delta V is equal to delta E over Q. Rearrange that to solve for delta E. We get Q times V, Q times delta V. So 1.6 times 10 to the minus 19 times 40,000 volts. What does that give me? 6.4 times 10 to the minus 15. And that would be in joules, right? If we're using standard units like coulombs and volts, then we're going to get standard units like joules. Now, it's not always the most convenient units, but they are standard units. Now, we got to convert that to electron volts. We know on our data sheet, On the left-hand side of our data sheet, it says 1 electron volt equals 1.6 times 10 to the minus 19 joules. So we're going to write that as a fraction. 1 electron volt equals 1.6 times 10 to the minus 19 joules. Well, that's going to be equal to x electron volts over 6.4 times 10 to the minus 15 joules. So if the top is equal to the bottom right there, then the top is equal to the bottom, if the top over the bottom, if the top is equal to the bottom, I was right the first time. If the top is equal to the bottom here, then the top is going to be equal to the bottom here. We just have to find out what the top is on the right-hand side. The 6.4 goes up by multiplying. We divide it by 1.6, and lo and behold, we end up with 40,000 electron volts, or 4.0 times 10 to the 4 electron volts. Now, it's the same number as we ended up with for potential difference. Is that a coincidence? Not really, but kinda. That probably didn't make any sense, right? It's kind of a coincidence, but not really a coincidence. In the last example we did, that wasn't the case. In this one it is, and it will be every time in this question. When we're dealing with an electron, the volts will always be the same as the electron volts. An electron or a proton. But when we're dealing with a charge like we were in the example of 3.2 times 10 to the minus 19, then the volts will not be equal to the electron volts. It comes back to the definition. An electron volt is is the energy gained or lost by an electron as it goes through a potential difference of 1 volt. So if we're dealing with an electron or something with the same charge as an electron, volts will always be equal to electron volts. I wouldn't memorize that. Okay, if you happen to catch that, that's great. But if you have to do the conversion, like we've done right here, for every question that you see involving electron volts, that's okay too. Okay, there's less to remember if you do the conversion. All right? Got a couple multiple choice questions for you, actually. Number 60. We won't bother submitting these just because time's starting to run a little bit short. So let's take a look at number 60 at your desks for a moment, please. Just as I expected, we got multiple people saying B. We got multiple people saying D. The answer is B. It goes back to the definition. The definition of an electron volt is the energy gained by an electron as it's accelerated through a potential difference of 1 volt. Okay. The energy gained by an electron as it's accelerated through a potential difference of 1 volt is 1 electron volt. So the answer is B. It's just the definition. Now, why did we say 1.6 times 10 to the minus 19? Well, because the energy gained in joules as an electron is accelerated through that is 1.6 times 10 to the minus 19. But that's joules, not in electron volts. All right? Yep. I'm sorry? Oh, yeah, right. You know what? I didn't even notice that. The fact that it's a proton. It doesn't actually matter that it's a proton here because a proton and the electron have the same charge. So that means the change in energy is Q times V. It's not related to the mass, it's related to the charge. So anything with the same charge as an electron will gain or lose the exact same amount of energy as an electron will, regardless of the All right. Oh, boy. This one's not so bad, but the 3 questions that go along with this diagram, the next 2 questions are a little bit tricky. Let's do this one first, see yourself. Okay. And I think we should be able to get this one. But then we'll unleash the challenge question for you. All right, the answer is A. Why is it A, though? Really? Good. Good. We got the charged object attracting the neutral object. There's no transfer of charge. There's no touching going on. It has to be induction. We're creating a temporary separation of charge in the fifth ball. Okay, that's why charged objects attract neutral objects. Okay, no touching, no transfer, got to be induction. The answer is A. Now the fun one. 62 and 63. The direction of the electric force on the fifth ball. We'll do this one as a group here real quickly here. The direction of the electric force on the fifth ball, well, if it's being pulled to the left, the electric force must be to the left, right? That's an easy question. B. But the magnitude of the electric force on the pith ball. How big is the force on the pith ball? Let's see if any of you, by chance, can get this question. All right, we're going to take a look at it here now. It says the magnitude of the force exerted by the pith ball on the charged Van de Graaff generator. So we're looking for that force right there. This is a tough question. I'll tell you what, when I see this question the first time, this appeared in 2001 or 2002, I can't remember which one, like a long time ago. That was the first time a question like this had appeared, and it was done very, very poorly around the province. Less than 20% of the people that wrote this exam got that question right, provincially. Okay, so basically, 4 to 5 or more got this question wrong. It's a tough question. When I saw it for the first time, I even struggled with it at first. I was trying to find the electric force. I was looking at it, F is equal to KQ1, Q2 over R squared. That was my first instinct, right? But I don't know what Q1 or Q2 is or what R, I do know what R is, I guess. But I don't know what Q1 or Q2 is. That wasn't helpful. So then I thought, well, wait a second. Maybe I could try the electric field experiencer equation. F is equal to Q times E. Okay, that's perfect. Okay, wait, I don't know what the charge of the pith ball is. Wait a second, it says it's neutral. I don't know what the electric field strength is. I don't know. I don't know. That doesn't work. So then honestly, I was at a little bit of a loss for a little while here. I was at a little bit of a loss. But you know what I do when I'm at a loss for things, and it happens from time to time that I'm at a loss as to where to start something. I try something. I just try things that are valid, even if I don't know where I'm going with it. I try it because every once in a while when you do that, a light bulb goes off after a while. Wait a second, this might actually work. The only thing that I could even think to do, and not because I knew this was going to work, but it was the only thing that I could just think to do, was draw a free body diagram. There's forces acting on this pith ball. There's gravity acting down. There's an electric force acting this way to the left, and there's a string acting this way. We'll call it Fs for the force of the string. And then I realized, wait a second, if this thing is at rest in static equilibrium, then the x component of the string force must be equal to the electric force, and the y component of the string force must be equal to the force of gravity, right? The x's have to balance, and the y's have to balance. So look, if I can find the x component of that force right there, then I've got the value of the electric force. It's just opposite direction, that's all. So let's see if we can do that. We don't know what y is, but, well, we do kind of know what y is. Y is equal to the force of gravity, so it's going to be 2.5 times 10 to the negative 4. Just wait 1 second, guys. Let's finish this. Times 9.81. What does that give me, guys? 2.45 times 10 to the negative 3. If that's the y component, I can turn around here and say tan 20 degrees is equal to the opposite side, 2.45 times 10 to the negative 3, divided by the adjacent side, which is x. X is equal to 2.45 times 10 to the minus 3, divided by tan 20 degrees. That gives me the x component of the force of the string, which is the exact same value as the electric force. Does that make sense? That's a hard question for you to get for the first time on your own. The good news is, okay, since 2001, a question like this has appeared probably 4 or 5 times. So it's not like it appears every time, but it's not completely irregular for it to appear either. The good news is, though, we've seen something like it now. So it's not so much of a surprise as it was that first time 12 years ago. All right. That's it. That's it.